Hopefully the last lecture gave enough perspective about why we don't want to solve the arbitrary optimization problem, why we don't want to have to optimize arbitrary functions subject to arbitrary constraints without somehow restricting the kinds of functions we can work with. Hopefully the last lecture proved that point to some extent. And so the question we have to answer now is, what restrictions do we have to impose on the way these functions we're optimizing can look before we get to a point where we have a path to get that right answer, to finding the solution to that optimization problem reliably with a computer program. And obviously, in a course like this, that's going to lead to us concluding that we want to live in the world of linear functions. But one more step, one really important step on the way there, is to talk about this notion of something called convexity, and to talk about something called a convex function. And often we think of what is called convex programming being one or two steps above linear programming in terms of difficulty to solve and likelihood of success when we're trying to solve it. So it rests on this definition, the idea of a convex set. And the word convex actually has the meaning you might expect geometrically. If you're familiar with concepts such as a convex hull, it's actually the same definition of convex. And it refers to sets of points. And so this is a set of points in Rn. But for the sake of visualizing it, it's actually fine to visualize. You can sort of intuitively think about it like a set of points in two dimensions. So here's my set S. And what I want to talk about is what it means for this set to be convex. And so a set S is convex, a set of points, if, when I choose any pair of points inside the set, so there's A and there's B, and I consider this line segment between A and B. And let's say I choose some value lambda between 0 and 1. What lambda really refers to is how far are you between A and B. So for example, if lambda is 0.25, so there's lambda equals 0.25, then I'm 25% of the way between A and B. And if lambda is 0.75, then I'm 75% of the way from A to B. And the set S is convex if, for any value of lambda between 0 and 1, any point that lies on this line segment. The set is convex if, for any point on the line segment between A and B, that point is in the set as well. In other words, what this is really saying is that the set is convex if, when I choose any 2 points inside the set, any 2 arbitrary points that are in the set, the entire line segment between them is also in the set. This is valuable for a lot of reasons. One of which I think I can point out early on is that the word convex means sort of what you expect it to. And we'll see in a few minutes that a set that looks like this is not convex. It has this concavity here. And of course, we'll be able to prove that by saying there's this line segment. There are 2 points that are in the set, but the line segment between them isn't entirely in the set. So this is not a convex set. And we might think, if we're talking about optimization problems, one of the issues we saw in the previous lecture related to feasible regions that look like this. Cases where we end up sitting over here on this arm of the feasible region, but it turns out there's something we want over here. And because we can't see between them, because there's some gulf between where we are and where we want to be, that can make optimization difficult. And it turns out that's one of the reasons why convex sets can really make our lives easier in an optimization setting. So here's some convex sets. These are, I think, sort of the stock examples of like the stereotypical convex sets. So here, and these are all examples in R2. These are all two-dimensional examples. So here I've got this set S1. And notice that if I choose any 2 points in S1, regardless of whether they're on the boundary or not, if I choose any 2 points, the entire line segment between those 2 points is always also in S1. The same is true of S2. There's no requirement that the set not have corners. So S2, of course, has these sharp corners here. It's fine, because if I choose any 2 points in the set, whether they're the corners or not, the entire line segment between them also lies in the set. And if I choose, I don't know, some interior point, that entire line segment lies in the set. And similarly, S3 is a convex polygon, and it is, well, I mean, I guess by definition, it's a convex polygon. It is a convex set as well. And again, we just have to apply that definition. Now, to be clear, to prove that a set is convex, we have to prove that this condition holds for every possible choice of A and B and every possible value lambda in the range 0 to 1, which is not as simple as just scribbling line segments onto a diagram. Obviously, we'll talk about how we write those proofs in a few minutes. And it is equivalent. The condition is equivalent that if I choose any 2 points, A and B, the condition is equivalent to saying that the entire line segment lies inside the set. Although it is true that this tends to be an easier condition to work with, working with it algebraically, than talking about line segments. Unless, I guess, if you're inclined to write proofs that are very geometric or construction proofs, perhaps the line segment approach could be helpful. But generally, it's usually easier to use the algebraic condition. It's also worth noting a bit of terminology. When I begin talking about this, about if I have 2 points A and B, and I refer to this particular expression, so lambda times A plus 1 minus lambda times B, if you look at that, you might notice this is actually a sort of weighted average, because lambda is between 0 and 1. Notice that if lambda is 0.5, we have 0.5 times A plus 0.5 times B. So this thing here, if ever I find myself taking one of these things, this is called a convex combination. And it shows up in a lot of places that aren't directly related to convex sets, because again, it is sort of an extension of the notion of a weighted average of these 2 points. And as I said earlier, if I were to choose a particular place along the line, so lambda equals 0.33, that would be about a third of the way between A and B. It's just a way of expressing a point along that line segment. And one thing, maybe this was obvious, but one geometric observation we should make is that if you are in a convex set, it doesn't matter where you are, so if I'm standing at any point inside of a convex set, there will always be a complete line of sight, that is, through points in the set, to any other point in that set. So if I'm standing at this point here, and I choose some other point, everything between me and that point also lies in the set. I have a line of sight. And again, if we consider those feasible regions that we had a problem with in the last lecture where there was no line of sight, we're guaranteed never to have that problem if our feasible region is convex. Now, let's talk about the examples of sets that aren't convex. So here we have S4, and I mentioned a minute ago that if you want to prove that a set is convex, you have to show that for every choice of A and B, the line segment between A and B lies in S. If you want to prove that a set isn't convex, all you have to do is find me one pair of points that can be a counterexample. So for S4, I can show that if I choose these 2 points here and I draw the line between them, then there's something on that line that doesn't lie in the set, therefore the set isn't convex. For S5 has a hole in it. Similarly, if I choose some line segment that crosses that hole, something inside the hole, that is not in the set, therefore the set isn't convex. And then S6, I guess I'll use these 2 corners here. And that entire line segment is actually outside of the set, and so S6 isn't convex. And the other slides are going to pretty much do that as well. And that's how we know these sets aren't convex. Now, of course, again, drawing on a diagram isn't sufficient. We actually have to write that out if that question appears on an assignment. And I'll talk a bit more about that process in the live session next week. So one thing we should observe is that the definition of convexity does not require that the sets look like this. This is our stereotype for what a convex set looks like, sort of the intuitive notion of it. But there are ways the definition can be met without the set conforming to our conventional notions of what a set of points should look like. So, for example, we have over here the set S7, which isn't completely open. That is to say, it's got this bounded edge, but it goes off to infinity in this direction. It just keeps going forever. Well, it's still convex because if I choose any 2 points in the set, regardless of where they are or how far away they are, the entire line segment is going to lie inside the set. So S7 is convex. S8, which is an infinite line, well, if I take any 2 points on this line and I connect them, well, that entire line segment is just a subset of my big line. So the set is convex. Everything on the line segment will lie on the line, and therefore the set will meet the definitions for convexity. So an infinite line, that's a convex set. In fact, if I have a finite line segment, that is a convex set, because the line segment, if I look at the 2 endpoints, the entire line segment lies on the line segment. And if I choose some subsegment of it, that also lies on the line segment. And so it doesn't necessarily have to have a non-empty interior to be a convex set. And then finally, there's this sort of degenerate special case, although not the most degenerate special case. We'll see in a few minutes there's an even more degenerate special case, which is a single point by itself. So a set of size 1, so we'll call this point P. So S9 is just a set of P by itself. Maybe I got to work on my curly brackets here. And you'll notice if you try to apply the definition, which is choose any 2 points in the set, okay, well that means that, A equals P and B equals P. There's only 1 point in the set, so if I choose 2 points in the set, I get the same point twice. And then I ask myself, if I take the convex combinations, lambda times A plus 1 minus lambda times B, what do I really have? Well, they're both, A and B are both just the point P, so I've got this. And you might notice that for every value of lambda, that's just equal to P, which is in my set. And therefore, S9 does fit the definition to be convex. It's a weird case, but it's valid. And so S9 is a convex set. The slides are going to take a minute to catch up to the point that I just made. It's worth noting, I guess, while we're talking about the line case, there's an observation buried in here, even though the line is an unusual situation. It's an unusual example of a convex set. There's an observation buried in here that arguably is the most important part of this lecture, which is that I can talk about this line being a convex set, and that begs the question, well, what about some other curve in space? So here's some other curve in space. This is not a convex set, because obviously if I choose 2 points on it and I draw the line between them, the parts of that line don't lie on the curve. It turns out that if I look at a curve in 2 dimensions and it turns out that curve is a convex set, it's going to have to be a line or a line segment. Other curves do not meet that definition. That's one of the reasons why, we'll see some of the advantages of convexity in a few minutes, that's one of the reasons why linear programming makes our lives so much easier, is that linear constraints are guaranteed to give us a certain set of properties that relate to convexity that we can't necessarily be guaranteed for other types of constraints. There are lots of ways of forming constraints that give us a convex set, but it requires us to actually check that property, whereas we're guaranteed that linear functions, so lines, for example, are going to be convex. Now, it's also worth noting that if I take the entire plane R2, so if I look at S equals every point in R2 or Rn, then S is a convex set. Because obviously if I choose 2 points in S, so two points in Rn, the line segment between them is also going to lie in Rn, because Rn is closed with respect to convex combinations. Okay, so what about if I describe some set to you? What if I ask you, here's a set, prove to me, so don't just scribble on a diagram, prove to me that this set is convex. So I give a set, I define it formally this way. So I say, I want a set of all points x, y, such that the absolute value of x plus the absolute value of y is less than or equal to 4. Prove that the set A is convex. So the set A geometrically looks like this. And to be clear, the boundary, this red boundary, is included in the set. So it's a closed set. It actually includes the points on the boundary. If I want to prove that A is convex, I have to prove that for every possible choice of the points A and B, the entire line segment lies inside the set. Or you could also phrase it as, for every choice of A and B and every possible lambda, the convex combination with those 3 parameters lies inside the set. I have to consider all possible ones. It's not sufficient for me to draw a line and say this line lies inside the set and therefore we're done. So how do I do that? I'm actually going to skip over this. I'm not going to go into much detail in this video. I am going to talk about this in the live session because I feel like it's the kind of thing that if you read over it by looking at the slides later, maybe you get it, maybe you don't, but it's probably better to talk about it interactively than for me to just pontificate on a video about it. So I can go over the broad strokes. The way I would prove this is I would say consider an arbitrary set of points P and Q in A. I'm not using the names A and B here because A is the name of my set. So choose 2 points P and Q. And then here are the coordinates of P, here are the coordinates of Q. Because P and Q were chosen arbitrarily, I can then just, if I show that for every possible lambda, the convex combination of P and Q lies in A, then I've shown that for every possible choice, the definition is observed, and therefore the set is convex. So I choose 2 points P and Q arbitrarily. And I observe that because they're in A, I have to have these 2 properties hold, because these are the criteria for membership in A. Okay, then I choose a value of lambda, again, arbitrarily. I don't fix it. I say, give me any value of lambda between 0 and 1 inclusive. Now consider this convex combination. We'll call it R. So R is equal to lambda times P plus 1 minus lambda times Q. And then just, remember this point. This is the triangle inequality applied to scalars, which I'm just going to state without proving it, although it's a basic fact that you've probably seen before. And then what I do is a bunch of tedious algebra. And so I say, let's consider, what I want to show is that, I want to show that the convex combination R is an element of A. But to be an element of A, that means I have to have this property. R, the x-coordinate, the absolute value of the x-coordinate plus the absolute value of the y-coordinate is less than or equal to 4. So what I'm going to do is tedious algebra to get to that point. So I say, let's consider Rx, absolute value of Rx plus absolute value of Ry. Well, R is the convex combination of P and Q, so it expands out to this. And I'm going to skip the steps, but there's a step where I apply the triangle inequality, and then a step where I apply the fact that lambda is between 0 and 1. And eventually I'm able to get down to the point where I can say that this is less than or equal to 4, and therefore R must be an element of A. And because I didn't dictate the choices of P, Q, and lambda, this proves it for all possible choices of those, and therefore A is convex. And again, I'll talk a bit more about that style of proof in the live session next week. So next one, this is an exercise that you might want to try as a character building exercise. This is talking about a circle of radius 2, and it's the set B, and turns out it's a convex set, and the question is, can we prove it? So there it is. There's a visualization of our set B. It turns out that, frankly, the proof is pretty much identical to this one, except I use different algebra, and I need quite a bit more of it. It's quite a bit more tedious because I've got basically x squared and y squared in there, which requires a bit more attention. But I use the same technique. I choose two arbitrary points, I choose an arbitrary lambda, and I show that that convex combination lies in the set. Okay, what about this one? This is actually very important. So I mentioned a few minutes ago there was this observation about lines that I said was one of the most important parts of this lecture. This is along the same lines as that. So this set C is the set of all points x and y such that x minus y is less than or equal to 4. If we visualize that, the key thing I want to observe here is that the boundary of this set, so the boundary is infinite. Unlike the previous two sets, the boundary is infinite. And this is the line x minus y, x minus y is equal to 4. And then everything on this side of the line is part of the set. So because of the inequality, everything where x minus y is less than 4 is also part of the set. And we're going to talk in the next lecture a lot about this particular type of convex set. It is a really big deal. And you might notice this is a linear function, and that's the reason why it's such a big deal. So the set C is unbounded. The boundary is infinite, but also the set just goes off to infinity in this direction. And so what we have to do is use essentially the same proof technique. We just choose two arbitrary points anywhere in the set, and we show that everything on that line segment is in the set as well. There are a few other clever geometric ways that we can demonstrate that. So we don't need too much cleverness because obviously it's relatively short. There's no weird absolute value shenanigans, no weird squares or square roots. But it's also worth considering there's nice geometric interpretation, which is that the boundary is a straight line. And if I choose 2 points on the same side of that straight line, how could a straight line segment between them cross that line? It wouldn't make any sense. The only way that the line segment can cross the line is if one of the 2 points is on the other side of the line, which would be a contradiction. So there's an interesting sort of clever geometric proof you could use there. But I don't see the need because really it's not too tough a proof just doing it straight up. So in this case, so C is convex. And of course, this is a big deal. This is a result that's parallel to that result about lines from earlier. If this weren't true, if C weren't a convex set, then the entire rest of the course would be worthless. We really need the sets defined by equations like this one to be convex for all of the theory about linear programming to make any sense to us. What about this one? So here's a set that I've defined, again, with a relatively simple function. X squared minus y squared is less than or equal to 4. But I'm saying the set isn't convex. And the exercise is show that it isn't convex. Now, when we want to prove that something is convex, we have to show that for every possible pair of points, the entire line segment sits inside the set. To show that something isn't convex, I really only have to find one example where the definition isn't satisfied. So if we visualize the set D, maybe you can see the problem. So the set D gives us this sort of hyperbola, or two hyperbola. And obviously, if I just choose 2 points here and I draw the line between them, we've got a problem. There's something in the middle that isn't in the set, so it isn't convex. So what I have to do is I have to show that formally. I actually have to choose, I have to provide 2 specific points that meet that criteria. There's a lot of ways I could do this, and a lot of times when people get a question like this, they really overthink it. They say, well, I could choose this point on the boundary here, and this point on the boundary down here, and then I could, okay, you could do that, but what is this point? Do you really want to find that point? How about we choose something more convenient? So why don't we just choose 2 points? Let's choose the point 4, -4. That would be, this is P here, and then this is Q. So we'll choose points with integer valued coordinates. And even better, you might notice that because they're mirrors of each other over the y-axis, then, or the x-axis, then the line between them, this point here exactly in the middle should lie on the line, and it should have the coordinates, 4, 0. And I can observe, and I should add, I mean, the usual problem with proofs on slides applies, which is, yeah, I had some time to think about this in advance to make a very clean, concise proof. There's no reason on an assignment that you'd be marked down for not choosing the cleanest possible representation. But in general, you should try and take whatever steps are needed to make your life easier. You don't have to choose points on the boundary as your sample line segment. You can choose whatever points you want. So why not choose points that have easy, convenient coordinates? So here, I choose 2 points that are definitely in the set, and just to clarify, you can demonstrate that 4 squared minus -4 squared is less than or equal to 4. So I choose 2 points that are definitely in the set, and then I take the combination of taking lambda to be 0.5, so halfway between these 2 points. I can show, just by applying the definition, that 4 squared minus 0 squared, because this is 4, 0. 4 squared minus 0 squared is 16, which is not less than or equal to 4. And that means that this point here is not in the set, and that means the set isn't convex. So I only need to show it for one point, one possible convex combination for the entire set to not be convex. What about this one? This is ridiculous. So I'm not even going to show a diagram of this because it won't really say anything. So the equation that defines the set is x squared plus y squared plus 1 is less than or equal to 0. And I'm hoping that at first glance you look at that and there's something seems off, maybe because we've used the very dramatic name Z for this, but something seems off, but it's not quite clear what. If we rearrange the equation, it might be more obvious why this is not going to, why there's something funny going on here. So if I move the plus 1 over here, what I'm saying is I want all points where x squared plus y squared is less than or equal to -1. And you might remember with real numbers, I would not expect either of these two things to be negative. And therefore, there actually are no points in Z. So just to be clear, the size of Z is 0. And then the exercise is show that that's convex. Now, if this were on an exam, people would start emailing me or whatever you do to ask questions during an exam. They start sending me messages saying, Bill, are you sure the exam question's correct? And then I'd have to be in that awkward situation of, like, do I answer and say, yeah, I'm sure it's correct, and then people know it's a trick question, or do I give some weird, vague response? So it says, show that the set is convex. Okay, so just like earlier with that set that was a single point, this is a really degenerate case. There are no points in this set. It is the empty set. So if I choose 2 points, if I say let A and B be elements of Z, well, let A and B be elements of Z is fine, but there are no such A and B. So I could say whatever I want. It's vacuously true. And so it turns out that's the issue. I can't find a counterexample, and therefore the set is convex by default. Because I can't actually pull 2 points out of the set to work with, you know, there's no way the definition could ever not be met. And so this is a case where the definition is vacuously true. Now, fortunately for you, because I've already talked about this, this will not be an exam question. And really, we don't care too much about the proving things are convex to worry about this special case much further. But it is worth noting that an empty set is a convex set. It's also worth noting that that actually is an important fact to know, because there are cases where, with our linear programs, where the constraint region is expected to be a convex set, we could end up with a linear program where there are no feasible points. That is to say, where the feasible region is empty. And it's nice to have that assurance that even if it's empty, it's still going to be convex. And so, yeah, this slide is saying what I probably just said, maybe more concisely. So here's some more facts. These are interesting things. These are the kind of things you might want to be able to prove by yourself, because you might be asked to prove a fact like this on an exam or an assignment. One key thing is that and this is, again, one of these driving forces for linear programming. We really need this fact for our understanding of linear programs to hold up. If I have two convex sets, their intersection is convex. That's a big deal. And so that means that what I could do if I have a complicated convex set is find a way of stating it as the intersection of a bunch of simpler ones. And it's automatically convex because if the things that I'm taking the intersection of are convex, the intersection itself is automatically convex. There's also this fact, which we're not going to need just yet, and we'll come back to it. It'll show up a couple of times in the future, but if I have a convex set and I take some affine combination, so I multiply it by a matrix and then add some constant vector to every point in the set, the result of performing that transformation, it turns out regardless of what the matrix is actually doing, even if the matrix isn't invertible or something, if I take all points, if I apply the transformation to every point in S, the resulting set Q is going to be convex. Now, it's worth noting that unlike many of the examples we've been working with, the actual the dimension of each point in Q could be different because I've applied some linear transformation. So it turns out S is in Rn. Q is actually a subset of Rm, where m could be larger or smaller than n, just because of the matrix multiplication that I've applied there. Okay, so that's a convex set. We also have a notion of something called a convex function. And convex functions have some properties that make optimization way easier compared to the general optimization problem we saw in the previous lecture. So what is a convex function? And if you've seen the definition of a formally linear function from a course on advanced linear algebra, so Math 311 or something, you might notice some parallels here, although we don't need that definition, so we'll leave that. That's just trivia. A convex function is a function where if I have 2 points and I take the value of f on some convex combination of those 2 points, the value is, and this is a key, less than or equal to the convex combination of the values of f on each point separately. So what you should notice here is that the convex combination is allowed to break out of the argument to f. So I can perform a convex combination before applying f, and the result will be less than or equal to applying the convex combination after applying f to each of the 2 input points. So if there was a noticeable edit in the video there, that was my PDF reader crashing, which is sort of rude, and I would have expected better. We're 2 lectures in, and it already can't handle it, so I can imagine how everybody watching this must feel. Anyway, I think what I was just about to say was, I was about to explain this disclaimer here, which is, if you've taken some advanced linear algebra course, you might know that this definition of a convex function doesn't have to be restricted to real numbers, but I'm going to do that here because as far as we care, we only care about real numbers. And we can see that there's already a lot of material, already a lot of symbols and algebra, and even the PDF readers, sort of had enough of this. So that's why we're not going to go into more detail. But if you want to talk about all sorts of other fun uses of convexity, I suppose you can come to the office hours. Now, back a few seconds ago, or a few seconds ago for you, I've had a few minutes to vent on the PDF reader that I've cut out of the video, hopefully. A few seconds ago, when I was talking about this definition, I wouldn't hold it against you if it felt like it was completely intangible. Talking about, I can take the convex combination before or after. I mean, yeah, okay, it's a symbolic definition. I guess it makes logical sense. It's very hard to understand what it means for a function to be convex. And I mentioned in the previous video, and I guess a few minutes ago in this video, that I am a huge fan of having a geometric interpretation of things. And arguably, I would not be able to understand definitions like this, or any of the definitions from today, without that geometric understanding. So for example, I know that a set is convex if every convex combination of points inside it is in the set. But for me, when I think of convexity, I think of that property, choose 2 points in the set, look at the line segment between them. If that always lies in the set, then the set is convex. So this definition is necessary, but there actually is a nice geometric interpretation. But to get to it, we have to go through another very odd definition. And it's of something called an epigraph. So this is an alternative definition of what a convex function is. So I take a function and I can I can construct a set called the epigraph of f. And this is a symbolic definition that's a bit ugly because it has to cover functions of in any number of dimensions, so up to n dimensions. What it's actually saying is take every point, every combination of x values and y value such that y is greater than the function value. And I can illustrate that on the diagram on the next slide. So here's a function that happens to be convex. So f of x equals x squared minus 4. What I want to do is I'm going to take every point on the curve and then every point above, on or above the curve. So I take a point on the curve and I take every point above that point. So I take another point on the curve, every point above that point, so I just keep doing that. What I'm constructing is a point set consisting of every single point on or above the curve of f. And I will painstakingly shade the whole thing in just to prove my point. There it is, and we'll just clean that up a little bit. That looks very nice. The PDF reader's lagging again, so I have a feeling it sort of seems to have indigestion with all the scribbling that I'm doing. In any case, fortunately for me, I can scroll to the next slide and look at the better diagram I have there. The epigraph of a function f is a point set constructed of every single point on or above the level of the function, so on or above the curve. And this applies in any number of dimensions, not just in this would be a 2-dimensional or maybe 1.5-dimensional example. This applies in any number of dimensions. The epigraph is the set of all points on or above the function. If the epigraph, which is a point set, if that is a convex set, then the function was a convex function. And that's how I think about convex functions, because I like the definition of a convex set. It's easy and tangible for me to talk about line segments in a convex set. So if the epigraph of a function is convex, then the function is a convex function. So that's how I think about that. You're welcome to visualize it however you want, but I think it's useful to know about this definition. So here are why convex functions are a really big deal. We saw in the previous lecture for the unconstrained optimization problem that we can always set the gradient to 0 and find inflection points and then do something with those to decide, okay, is this a local minimum or a local maximum? And then cross our fingers and hope that we choose the right one to be the global minimum. But there could be an infinite number. We may not be able to find the global minimum. But that's not true in a convex function. In a convex function, if you find a local minimum, it is always the global minimum, period. So that's it. And what's great about that is we have conditions to find local minima. And if we find one, then we're done. We're home free. If it's a convex function, whatever local minimum we find, that is the global minimum, guaranteed. So that is a really big deal. And that means if we can work with convex functions only, we suddenly don't have to worry about this problem of looking at an infinite number of inflection points or something. It's also, I should consider the fact that we just showed that this is a convex function, x squared minus 4. X squared minus 4 is a quadratic, and we could establish that you could look at polynomials of other degrees, and they in many cases are convex. So we're not giving up too much. There are non-trivial convex functions out there, and as it turns out, linear functions are also convex. So this actually allows us to very easily solve the unconstrained optimization problem. It really simplifies unconstrained optimization compared to what we saw in the previous lecture. Okay, sorry, I missed the slide, but the slide agrees with me. It's a really big deal. So what about the constrained optimization problem? It turns out that there is also a set of conditions that saves us there as well. This is obviously really nice, just having this fact, you find me a local minimum, you've got your global minimum. It's a bit more complicated for the constrained problem, but there is a way of being able to tell if I found what looks like a minimum, so a local minimum of the constrained problem, There are a set of conditions that if they hold, I know I have found the final minimum of my constrained problem. There's no chance that some better minimum is hiding around the corner. And this is a set of conditions called the KKT conditions. So Karush, Kuhn, and Tucker. And we do not want to belabor this point. I'm actually not even going to show the KKT theorem because it's very complicated. It's not as concise as this fact from the previous slide. We will come back to them a couple of points in the course because actually it turns out that many of the things we rely on for linear programming do secretly rely on the KKT conditions. I'm hoping that a graduate student at the end of the semester does a presentation about convex optimization so we can hear more about the KKT conditions. But these conditions allow us to decide whether a particular point of interest that looks like a minimum is indeed the optimal solution of a constrained problem like this, under the condition that every single function involved is a convex function. And obviously, I guess the way I've framed it here, that these are all constants. So here's an example of that. I have this constrained optimization problem where it's over functions on two variables, and both my objective function f and the single constraint that I have, g1, are convex functions. So that means that I will be able to employ these KKT conditions. So first, let's take a look at the objective function just by itself. Now, the objective function f does have a global minimum. It is somewhere up there. It's not actually on the plot because it turns out the feasible region doesn't contain it. But f does have a global minimum where the gradient equals 0. It's just that we will not really have much interest in that because the feasible region is this ellipse. And so the global minimum of f is up there somewhere. It's not going to be of interest to us. The actual minimum we want is somewhere in this area. And also, if we care, the maximum with respect to this constraint region is somewhere over here. So f is not a linear function, but there is a certain, I guess, relatively linear-looking relationship between the minimum and maximum with respect to this ellipse. And so the KKT conditions are stated in terms of derivatives. They actually talk about the gradients of the objective function and all of the constraints. So here is the solution to the minimization problem. It lies right here on the boundary of the feasible region. That shouldn't surprise us because we know that if we have a constrained optimization problem and the objective function isn't unbounded, the solution is either going to be a strictly interior point or it's going to lie on the boundary. And we know that there are no minima of the objective function in the interior, and that means we should expect that the minimum will lie on the boundary. If we take a look at the gradient of our objective function and the gradient of our constraint g1, it turns out that they have opposite directions. Now, the slide isn't clear about this, but they don't necessarily have to have exactly opposite magnitudes. We're not guaranteeing that gradient f equals negative gradient g, but it turns out that at this minimum, we can expect that they will always have diametrically opposite directions. One will be in the same direction as the negative of the other. And it turns out at the maximum, we get something similar. They're parallel. So at the minimum, the gradient pointed in the exact opposite direction of the gradient of f pointed in the exact opposite direction as the gradient of g. At the maximum, the gradient of f and the gradient of g are parallel. They point in exactly the same direction. Now, let's consider this variation. So in this case, that's sort of an interesting observation, but there's only one constraint, this function g that describes this ellipse. It's interesting to observe that for some reason the gradient of g and the gradient of f seem to observe a particular relationship at the minimum and maximum, but it's not as obvious why this condition is helping us unless we look at what happens with multiple constraints. So this is the same problem, but I've added two more constraints to it. So the first two things, the objective function and g1, are the same, but I've added in two extra constraints which will give some more nuance to the way our constraint region looks. So now the constraint region looks like this. These bits here are still, this is the curve supplied by g1. These other two things, these other two walls I've added, these are these two new constraints. And I've done this because I want to see what happens if our minimum and maximum occur at these corners. So the constraint region actually has these vertices, these corners where two constraints meet up, where they intersect. And as it turns out, I mean, obviously deliberately, it turns out that the minimum and maximum of the constrained optimization problem lie at those corners. Let's take a look at what happens if we if we expand that out. So here is the minimum. The minimum sits at this corner here. Let's take a look at the gradient of f and the gradient of each of the two constraints that apply. So in this case, this would be the gradient of g1, and this would be the gradient of g3. g2, that's this curve here. And so g2 has nothing to do with that minimum because g2 is not one of the operative constraints at that point. It's not one of the constraints that's being met at equality. So here's the gradient of g3, here's the gradient of g1. I want to observe the following thing. So the gradient of f is no longer diametrically opposite to either of these two things. But if I look at the negative gradient of f, so I go out this way, this would be negative grad f, notice how it is sort of a positive linear combination of the two. It lies between them. That's a big deal, and that's as close as I'm going to come to describing the KKT conditions in this lecture. The KKT conditions tell us that a point is the minimum if the negative gradient of f is lies somewhere between the gradients of all the constraints at that boundary point. And actually, more generally, it says something like, if you can create a linear combination of all of these things with positive coefficients, so we call that, we'll say maybe c1 times this, c2 times this, gradient of g1 plus c3 times the gradient of g3. If you can get 0 out of that, and you also have the constraints that c1, c2, and c3 are all greater than or equal to 0, then the point you're looking at where that holds, that is the minimum you were looking for. So the KKT conditions tell us that if you can form a certain type of linear combination, then you are guaranteed that what you are looking at truly is the minimum. I know that there's a lot to digest there, especially because for some reason I'm obstinately refusing to show you the actual theorem. It might be more obvious if we take a look at the maximum. So the condition for the maximum is basically equivalent, just with the sign flipped on the gradient. So there again is the gradient of f at the maximum point. Here is the gradient of g1, which is the ellipse, and here's the gradient of this line segment, which is g2. Notice again that at this maximum, the gradient of f, the direction of the gradient of f, lies between the directions of the two constraints that are operative there. More generally, it can be formed as a positive linear combination of those two vectors. So some multiples of those two vectors, positive multiples added together. The KKT theorem tells us that if you get into that situation, if you find a point where the gradient on the boundary where the gradient of f is a positive linear combination of the gradients of all the constraints that are relevant at that point, then you are looking at the maximum. And again, lots to digest there, but think about that. That's a condition that you can test. If the condition holds, you're good, you've found the maximum. There isn't a concern that maybe there's some other maximum hiding somewhere else that you haven't found yet. And it's also worth noting, just like we saw in the previous example, let's scroll way back. In this example here, we had our gradient of g1 and our gradient of f. This point is not the intersection of multiple constraints. It's fine for the maximum to occur somewhere that isn't a corner, and that could happen in lots of cases. The KKT theorem still applies. It says we want a positive linear combination of the gradient of f and all of the constraints that do apply, that are being met at equality. So if you're sitting at a corner, then there might be two or more constraints that apply. If the maximum were, for example, here, you would consider the gradient of f, which in this case actually points off here, and the gradient of g2, which probably points somewhere down this way. And so in this case, the KKT theorem would tell you this is not your maximum, because you can't make the gradient of f by taking some multiple of the gradient of the only constraint that applies, which is g2. So we will come back. It turns out the KKT theorem is very significant to many results in this course. We don't really need it in its full force for most of the course. Although, as I said, I'm hoping we can come back and see it in behold its glory at the very end of the course after working for a few months with linear programs only. And so the slides, I guess, are now... the slides are basically saying what I just said, which is that in general, you can expect that at a minimum, the direction of negative grad f, which would be this vector here, will be a positive linear combination of the gradients of all applicable constraints. So that's all constraints that are met at equality. Remember that our optimization problem looked like this. Gi of x is less than or equal to b sub I. When the constraint is actually met at equality, then you'll get it equals b sub I. And what the beauty of the KKT theorem is it says if you can prove this relationship holds at a point, you've now found the minimum. And similarly for the maximum. You found it, you are done. You have nothing left to prove once you can apply the theorem. The slides are saying we'll wait until later. In a course like this, so crammed full of stuff, we may never get the chance to cover it in full. I really hope we do, though. And so because we have this, we can now find the minimum algorithmically by just solving the conditions of the theorem. Now we haven't seen the conditions in full, but the conditions could still require solving nonlinear equations if the functions we're working with happen to be nonlinear. And it turns out that when we work with linear functions, applying the theorem directly is possible, but probably still a bit cumbersome for a variety of different reasons. And so this is pointing out that convex programming, so solving optimization problems where our functions are guaranteed to be convex, is now a great deal more tractable than the problems we saw in the previous lecture because of the KKT theorem. But I still have to solve nonlinear systems and I have to compute gradients and things if I want to work outside of, let's say, a linear setting. And so what we have to do now is we actually have all the tools we need to build optimization problems that are imminently solvable, where we can take the problem and we know that we can find the answer. We know that if we work inside of convex systems, so systems of convex functions, we can use the KKT theorem, we can use that observation that any local minimum is a global minimum of the function. But what we need now is the ability to compute and work with our functions conveniently, something that we don't quite get with arbitrary convex functions. And I mean, the spoiler is obviously linear functions are going to be the solution, and we'll begin talking about the geometry of linear programs in the next lecture.